Welcome everyone. Today the speaker is Giuliano Basso. He's going to talk about absolute Lipschitz extendability and projection constants. Please, Giuliano, go ahead.
So yeah, hello everybody. Thanks for coming. So some of you already saw me talking about this a year ago, but the results changed a little. So I still hope it's still interesting. So what I will talk about is basically something I discovered while I was writing my dissertation. And yeah, the story goes like this. So here we have metric spaces. And in this rectangle here, we have Banach spaces. And yeah, here, for example, could be finite metric spaces. Or yeah, could also take doubling spaces, Carnot groups, and yeah, injective spaces, and many other classes of spaces. And here we have, let's say, small L infinity. We have polyhedral Banach spaces. We have also C0 or Sobolev spaces, and so on. So, and the basic idea is that there is a functor from here to here, which is called Lipschitz free spaces. So basically you have X, a metric space, and you assign to it a Banach space, which is called f of x, which is called the Lipschitz free space. So this is a Banach space. And yeah, the construction here is very analogous to the one to the construction of a free group. So where you have the property that when you have x and y, and then you have a Lipschitz map F between x and y, and then there exists a linear map F between the Lipschitz free spaces, such that this diagram commutes. Here, F Lipschitz, and the big F is linear. And you have that linear with the norm of F is equal to the Lipschitz constant of the small f. So that's the basic idea, to have a metric space, and then that's called linearization property. So the basic idea is you have a metric space, and then you linearize it with the Lipschitz free space, and then you can work in the category of Banach spaces. And I will now state my result, and then I will try to explain what all the symbols mean. So theorem, we have X is a finite metric space. Then we have that the absolute Lipschitz extendability constant of X is equal to the projection constant of f of X in some large ambient space, which is in this case is the free space of little c0. So this is the theorem. And yeah. So here, this is the absolute Lipschitz extendability constant. And this here will be the projection constant. Yeah, and as you saw before, this here is the Lipschitz free space. So maybe one word why this theorem can be useful. It's like so this side here, this AE of x is very hard to compute. So I mean, you will see it's like the definition is very, yeah, you have a lot of free variables. And but this side here is in some situations, it's actually computable. You can just use your computer to compute this side here. So so this actually gives us a application. A corollary of the theorem is just two exact results. We have that this quantity here is 4/3, and this quantity here is 5 + 4 square root of 2/7. Yeah, but this doesn't have to concern us right now. We will just see this later, that this really, we really get these exact numbers due to this constant here. So now I think it's a good idea to talk about Lipschitz extension problems. So Lipschitz extension problems. So the basic setup is as follows. We have a metric space X and a Lipschitz map to another metric space F at a C. And our space X lives in a bigger space Y. So we have X, Y, and Z metric spaces, and F Lipschitz, a Lipschitz map. So, and the question is basically, once you have this input, so that's the input, and then the question is, does there exist a map F bar such that the diagram commutes, which I write like this. So, and basically, we're also interested in a quantitative version of this. So we are interested, does there exist a map F bar? And if yes, what is the smallest distortion? So we can ask, so we can definition. We define E, X, Y, Z, F. So that's all the input. So this is the input. Smallest constant. D bigger than 0, where D stands for distortion, such that exists F bar making the diagram above, so this star here, making star commutative, and we want that the Lipschitz constant of our map F bar is smaller than D times the Lipschitz constant of F. So this is the important inequality. Basically asks that we want to make the distortion, that's this guy here, distortion, small as possible.
Giuliano, in general,
Yeah.
the constant also depends on how you embed x into y, correct?
Exactly. Yeah. Yeah. It's really that's really true. Yeah. I should also point this out in the input of the data. That's true. Yeah. But it's sort of implicit in the once I chose y. Yeah. Yeah, that's true. That's true. So okay. So let me continue by explaining the general theme. So general theme. So basically, we have this input x, y, z, f, and we fix some of it. So fix some of the variables x, y, z, f, and let the others be arbitrary. So yeah, arbitrary means free. And once we have this, so we fix some variables and let the others be arbitrary, and then we take the supremum over the free variables, and then take supremum over the free variables. So yeah, that's to keep in mind. So basically, we have the input, and we decide to fix some of it, and the other thing will be arbitrary. So, and there are three main classes of three main way of doing this. So let me start with the one that has been considered first historically. So the first one is fix y and z, and we define e y z as the supremum over e x y z f, where xf as in star. So okay, maybe let me go back to the diagram. So we have y and z is fixed. So y is fixed, z is fixed, and then we basically take any subspace of y, so any x, and so then the embedding doesn't matter since x is y is fixed, and we just take any isometric any subspace of y, metric subspace of y, and f is also varied. So that's the first. That's historically the first notion that has been considered. And let me just give let me tell you some major results. So the first one is, that's the first actually in this direction from McShane. 43 tells you that EY, you can extend any Lipschitz map into the real numbers with distortion 1. So this really tells you that you have a Lipschitz map defined on the subspace of a metric space, and this function actually goes to R, and then you can extend to the ambient space with the same constant. So that's the first result. And the next result is
Giuliano,
yeah.
the fact that this E was defined as an infimum, this doesn't really, I mean, if you state it like this, E equal to 1, doesn't mean that there exists a map.
Yes. Yeah. Yeah, that's absolutely true.
Or is it clear that infimum is actually a minimum?
Let me think about it. I would say in general, no. But in the situations we will consider it, most of the time it is attained. But that's true. I mean, that's sort of the drawback of this notation, actually. That, yeah.
Suppose if you have like some compactness, or I mean, you can use Arzola-Ascoli type arguments, but this is of course only if you can somehow control this minimizing sequence.
Yes.
Because of course, yes. I mean, in general, they need not be equibounded or anything like that.
I think if the target space is proper, then I think then it should work. Then it's
but
attained.
Even then, well,
yeah. Probably you need some homogeneity in the target as well.
Ah, maybe. Yeah. I mean, I think most of you know this Max-Schein result, and there it's really very explicit actually how to construct the map. There it's really just I can write. Maybe not. We don't want to lose time, but there it's really a one-line proof more or less. It's Hahn-Banach for Lipschitz functions. So okay, let me continue with the next one. This is Kirschbraun. Yeah, and this tells you that you have H prime is 1, where these two spaces are Hilbert spaces. And yeah, there the proof is already a little bit more involved. But maybe one important thing to say is that the constant is still 1. So once you have shown that you can extend to one additional point with constant 1, then you're almost done. Then you can just iterate the procedure. So these are two results which give you constant 1. And but then historically it emerged that it's also interesting to consider spaces where the constant is not 1. So I will give you just 1 or 2 results in this direction. There are many results. I cannot state them all. So theorem Ball from 94, which tells you that E from L2 to LP is smaller than 6 divided by P minus 1. So, and it's actually open conjecture if E L2 L1 is smaller than infinity. So you see when P approaches 1 here, then this blows up. Yeah, and of course this is for P bigger than 1. So, yeah, okay. Okay, that's good.
Giuliano, is that for LP spaces over the unit interval, or is this like for any measure space?
For any measure space.
Okay.
Yeah. Yeah. It has to do with in Banach space theory, there's this notion called cotype and type, and it has to do that these spaces have so that LP has cotype P, and then yeah, that's general for any measure space. So okay, did this result, and maybe the last one, I think not many people know, from Carlton from 2005, which tells you that EY to the continuous functions on a compact metric space is smaller than 2 with equality. For the small C0. And for any metric space Y. So this, if you know the notion of a retract, this tells you that CK is a absolute 2 Lipschitz retract. And yeah.
So with the quality, you mean when Y is C0?
Yeah, no, when CK is C0.
But it's an abstract condition on the compact space, right? Because
so Y is arbitrary.
yeah.
So for all Y, you have that you can extend any Lipschitz map to CK with distortion 2.
But CK is the space of continuous functions on continuous bounded functions on a compact space K, or not?
Exactly. Equipped with the supremum norm.
Right.
So
it's
you
not always clear when. So I mean, what choice do you make to have this CK equal C0?
You take the okay, that's actually a good point. You take the compactification of the natural numbers, the 1-point compactification. This is still metrizable, right? And
really?
Yes, because it's only. Oh, maybe I'm wrong.
What compactification depends on that, I suppose.
I think the 1-point compactification.
Okay.
Of the natural numbers.
All right. Fair enough.
I think it's. But to be honest, I haven't.
Yeah,
but it's certainly true that the statement is certainly true for C0. Maybe I should say it this way.
Yeah.
If I write C0 instead of CK, then it's true.
Mm-hmm. Okay.
And I'm sort of convinced that C0 is a CK space.
Yeah, but you have to remove.
But yeah.
Remove the constants.
So, Giuliano, what space Y do you take for equality? Because I mean, of course, if you take Y equals to R, then you're going to have the constant 1, right? E will be 1, even with C0. So what is Y there? Or
the L infinity. So you have
okay.
You have that the small C0. That's actually a good point. Lives here, right? This I mean, this is just xy and the limit of xy goes to 0. And this lives in the small L infinity, and the projection from L infinity, any projection from small L infinity to C0 has constant at most 2. At least 2. That's the. So for E L infinity, C0 is 2. Which is maybe a little bit confusing in this. Yeah. So the ambient space is L infinity. So we have C0 lives in L infinity. Here we have the identity. Yeah. So now that's the. Yeah. This gives you 2 at least. Okay. Yeah, so I think it's a good idea now to move on. I convinced you that this notion here, this EYZ has, there are many theorems. And now let me talk about the second class of extension moduli we want to consider. So here we fixed y and z, and now we fix the target, fix z. And we set, the notation will become clear in a moment. Lambda of z is the supremum over y of EY C. So it's just, this means that we fix the target and we everything else is arbitrary. And maybe now I can state, so I use the letter lambda, and this is no coincidence. So there's a theorem of Lindenstrass. From 64, which tells you the following. So we have, if C is a dual Banach space, so this just means there exists E such that the dual space of E is equal to C. And then we have the following. Then we have that the big lambda of C is actually equal to the projection constant of C. So this thing here, I will define it shortly. It's called the projection constant. And it's nothing but the same as the big lambda, but in the category of Banach spaces. So you only consider linear maps and not Lipschitz maps anymore. So, but let me define it. So this is the theorem, and definition for Banach spaces E which lives in F, we set lambda EF. This will be the smallest norm of a projection from F onto E. So the infimum of the norm of P, where P goes from F to E, linear and surjective, and P squared is P. This just means that, this means that P is a projection linear. So the linear here is really the important thing. So here we only consider linear maps. And you see here the little lambda has only one slot. So the idea is just to take the supremum over all ambient spaces.
But you are not dependent on identity, are you?
Sorry?
Are you assuming that this P restricted on E is the identity?
This follows from, you know the map is surjective, and then on the image you are the identity. This follows from this here. I mean, this tells you basically, once you're in the image, you can apply P again, and then it's still the same point. So on the image, you really need the identity.
Mm-hmm.
And yeah, maybe this is not the best way to write it, but it just means that you have I can draw the picture.
It's fine, it's fine.
But yeah, just quick. It's you have F and E, and you do this. So that's what happens linearly. Okay, so I did this for an ambient space F, and now once again in this business we take the supremum. Lambda E is the supremum over F. Yeah, that contains E. Lambda E F. But yeah, this looks, I mean, you take any ambient space and this looks really hard to compute. But the good thing is that this is actually the same as lambda E small l infinity, provided that E is separable. So we can, in principle, we could, this could be the definition. Okay. And now Lindenstrauss tells us that the small lambda of C is equal to the big lambda. So okay, this is the statement. And I think I have to quickly remark that the little lambda actually is you can compute it with using Mathematica, for example. You can use your computer to compute it. So a remark. If C, so the Banach space C, is polyhedral, and this just means, yeah, for today, this just means that the unit ball is a polytope. Then this follows directly from the definition. Exists an integer D such that C lives in L infinity D, and lambda C is lambda C of L infinity D. And the good thing is that to compute this, one can actually solve a linear programming problem. It's really just one only has to solve. Linear programming.
Are you assuming that Z is finite dimensional?
Yes. Yeah, definitely. Yeah, that's a good point. So C dimension is more than plus infinity. Yeah, that's true. I mean, polytope in infinite dimension is a little bit, it's a tricky notion, I would say. I mean, there, of course, you can still define it, but yeah. So here it's really, for this to make sense, C has to be finite dimensional. And once you have this, then you can compute lambda c directly with your computer. And basically, if C is infinite dimensional, then the standard definition of polyhedral says that any finite dimensional subspace is polyhedral. And then you can just, okay. But yeah. Okay, so this is this remark. We can compute it, and for us today, important for us today is that note, as we will also see this, that if X finite, then the free space of X is polyhedral. So for finite metric spaces, we can really compute the projection constant of the Lipschitz free space. Okay, good. So yeah, this is now maybe I can go back to our goal for today. So you see, I need to define 3 quantities: the absolute Lipschitz extendability constant, this one here, and the projection constant, which we now know, and this Lipschitz free space. So the next thing I will do is to define this absolute Lipschitz extendability constant, which is basically the only case left we haven't considered. So here we fixed C, and we more or less fixed Y and C. And now a sensible thing to do is only to fix X. So that's the third case you have to consider. 3, fix X. And we define
Giuliano, can I just ask quickly something?
Yeah, sure. Yeah, sure.
If I'm interested in computing little lambda of Euclidean R2, can I somehow do that by approximation via polyhedral? I mean, do you get the formula, a thing that converges afterwards?
Yes, that's one possibility. You can just approximate your unit ball with polyhedral. But I realized recently that actually there it's easier when you just embed R2 into small L infinity.
Oh, okay.
And then there is a symmetry argument that helps you to
maybe you can explain it to me once.
Oh, yes.
Yeah. Okay, thanks. Okay.
Okay. Maybe, but sorry for this, but here before, if you remember, we had Carlton's result that, let me just state this. This we had with our new notation. It's just a small remark. We have that big lambda of C0 is 2, right? This I mean here Y is arbitrary, and then C0 is a Lipschitz retract, but the small lambda of C0 is infinity. This is actually, this is not easy to see, but this is a theorem of Sobchik from the 40s. So Lindenstrauss's result is not true for any Banach space. It's really, there has to be an assumption. So here in the theorem of Lindenstrauss, I can put them together. Here we had that C is a dual space. And if you want this results here in the box, give a very, very high level proof of the fact that C0 is not a dual space. That's, if you, okay, good. So, but let me continue. Now we're about to define the absolute Lipschitz extendability constant. And this is just, as you would guess, probably it's the supremum over all Ex, so X is fixed, Y, C, and F are free. So Y, C, F as in star. So I could stop here, but the problem would be that I have to somehow restrict target spaces. Otherwise, this constant will always, in many cases, will be infinite. So we restrict ourselves to and C Banach space. So this is we need this needed that Rx small infinity for interesting cases. So, okay, so this is the definition. And let me just state the state of the art concerning this constant. It's a theorem of Lee and Naor, which tells you that, so there are two things. The first thing is if X doubling with constant nx, then we have that the absolute Lipschitz extendability constant of X is smaller than an absolute constant times the logarithm of n of X. So, and this result is almost sharp. So let me just quickly state this conjecture. Which is also due to, that's from 04, sorry, I forgot. This conjecture is also due to Lee and Naor. Basically, it says that AE of X is smaller than C, the square root of the logarithm of nx. So, and this estimate here, this would be sharp asymptotically. I mean, the constant, if you disregard the constant, because sharp, because you have that AE of Rn is equal to the lambda of Rn. This is, yeah, that follows directly from the definitions. And this, as we know from Lindenstrauss, is small lambda of Rn. And we know that small lambda of Rn is bigger than the square root of 2 over pi. That's not so important. So some constant times square root of n. So yeah, and you know that, yeah. This is due to Grünbaum.
Giuliano, if one applies the Lang-Schlichenmeyer theorem, what constant or what value will one get? So because,
that's a very good question. Actually, I'm not sure, because in their proof, the constant is really implicit. But I think it would be a good project to really see what the constant is they're getting. But I would suspect it's not the logarithm of the doubling constant. I think it's because, I mean, they have much more general target spaces. They have here, it's really Banach spaces. And in Lang-Schlichenmeyer, they use Lipschitz K-connected, which is, yeah. So their construction really
but that would just mean that the Lipschitz connectedness constants, they're all basically uniformly bounded, I guess.
Ah,
right?
yeah, that's true.
Probably.
You should use the Schwarzschild doubling theorem. No?
Yes, but yeah, doubling implies that it's finite. That's what Nagata dimension, right?
Yeah, but
Yes.
Lang, Schlinck, and Meyer, they're embedding in product of trees, not in Banach spaces. Right?
No. They have their extension theorems, and that in particular in this setting, right? If you have a finite metric space, finite Dassault Nagata dimension, you have a target space that is Lipschitz connected up to the Dassault Nagata dimension +1, I think. Then you can always extend Lipschitzly. That's their theorem, right?
Yes. Yeah, they sort of factor through a Hilbert space, more or less. That's what they're doing. And then, yeah, extend it successively. And here the Lee-Nauer proof is really different. So they use some results from theoretical computer sciences. Okay. So yeah, but I really think that the Lang-Schlichen-Meyer constants are probably some powers of the doubling constant, not of the doubling, of the Nagata constant. This I would guess, but I don't know. I always wanted to check. So okay. So this was just a remark. And now for us today, important is, so that's the first part of the theorem. For us today, we care about, here it's about doubling spaces, and we care about finite metric spaces. So AEN is defined as the supremum over all x of cardinality n of AEX. So once again, I take another supremum. It's just here x is fixed. Okay, the constant here is independent of x, and here we only fix the cardinality of x. And then we have that AE of n is smaller than c log n. So as you would expect from here, but they improved it to the following. It's log n. So yeah, this is the important estimate. And yeah, up to now, I think that's the best asymptotic result there is for this quantity here. So
who is it from, this estimate? Who proved that?
It's still Lee-Nauer.
Okay.
I'm sorry. Let me highlight it. So okay, but now, yeah, okay. Now I also talked about this absolute extendability constant, and they're very strong asymptotic estimates with a conjecture which I really believe to be true. So this would be sharp, and they're very low. There are some lower bounds that come close to it. So, but what we don't have is, like, there are no exact results. So no exact results so far. So only AE1, 0, and AE2, 1 are known. And yeah, for today, maybe I will still have time. For today, we have also AE3, 4/3, and the other one, AE4, 5 + 4, square root 2/7. So, but I guess I will only be able to show you this quickly. So now we have defined the absolute extendability constant. I have defined the projection constant. And the last thing I want to define is Lipschitz free spaces, because we need them to understand our result. So Lipschitz free spaces. And maybe I should point out there's a lot of there's a lot of current research on those spaces, because they really are also interesting from the point of view of a Banach space theory. So let me define them. So we define Lipx is just Lipschitz functions f from x to r, f Lipschitz. And this is a R vector space. With semi-norm. The semi-norm is just you take f lip will be the Lipschitz constant of f, and semi-norm because the Lipschitz constant function this is 0. So I mean a constant function has Lipschitz constant 0, and then now we define definition. The Lipschitz dual is just x sharp is lip x to quotient out the constant function. Equipped with the Lipschitz norm. So that's, and the notation here, this sharp here, is no coincidence. It's really there to indicate that this space is a dual space. So there's a general result from functional analysis which says that there exists Banach space C such that the dual of C is X sharp. So, and this is true for any metric space, no restriction whatsoever. Then this tells you that the X sharp, which is called Lipschitz dual, the Lipschitz dual is actually a dual space. So, but yeah, this is okay. It's an abstract result, but one can do better. One can actually, I can give a construction for C. So let me quickly do this. So, suppose, just to make it easier, suppose X bounded, and we set f of X. So now I can finally define it. This will be the Lipschitz free space, is the set of all signed radon measures. Signed radon measure such that the total mass of X is 0. That's our space. That's for now that's a set, and we can define a norm on it, which is called the Kantorowicz-Rubinstein norm. So set the norm of nu Kantorowicz-Rubinstein is just the supremum over all F in Lip X with Lipschitz constant smaller than 1, and we take the integral over X F d nu. So that's, and maybe I can write it more clearly. So sup F integral over X F d nu plus minus integral over X F d nu minus. So I decompose my measure nu into a positive, and I use the Hahn decomposition, and yeah. And here you see already from this definition, since the total mass here is 0, it doesn't matter if I add a constant here to F. So it's really, I only care about Lipschitz functions up to a constant, right? If I add a constant C, this constant will cancel out due to the, since nu plus of X is nu minus of X by assumption, okay. So in this setting, fact, the dual space of F, so Fx is equipped with this Kantorowicz-Rubinstein norm, Fx dual is the Lipschitz dual of X. Okay. Okay, maybe let me quickly remark one last thing. Fix x0 in X. Then we have that the map delta from X to f of X, which maps the point X to this signed measure here, delta X minus delta X0. This is an isometric embedding. And yeah, okay. And then by construction, we have that when we have a Lipschitz map from X to Y, and we have those delta embeddings f of X, then f of Y, then here we can take f of nu is just a push forward measure. And if you choose your deltas correctly, then this diagram commutes. I mean, you have to take care of this point here. So here you have to, I can write it here, you take delta x0, and here you take delta f of x0. Okay, and then this diagram commutes by definition. And short calculation. We have that the norm of f is equal to lip of small f. So that's what we wanted. Okay, so now I defined Lipschitz free spaces, projection constants, and absolute Lipschitz extendability constants. So now let me maybe go back to the main result. So So this result here really tells you that this constant here is nothing but the projection constant of the free space as a subspace of the free space of C0. And by definition, so I have to erase this here quickly. This implies, in particular, this implies AE of x is smaller than lambda of f of x. That's the corollary. I mean, this notion here can be hard to compute, but this notion here is, as I maybe can convince you shortly, is sometimes not that hard to compute. So I think I will use 10 minutes or so, maybe, if you want to show you. So I will show you AE3 equals 4/3. This I can this I can show you quickly. So so having this theorem at hand, so suppose that maybe let's, yeah. So suppose we have the theorem, and then we compute AE3. So corollary AE3 is 4/3. So okay, let me start as a proof. Let me start with a fact. So we can define lambda n as the supremum over lambda c, where the dimension of c is n. So I fix the dimension and everything else, and the space is arbitrary. Then the sup is attained. And we have an upper bound, and lambda n is strictly smaller than the square root of n. This is due to Koenig and Lewis from 1984, and this is, I think that's the best asymptotic estimate there is. But similarly to absolute Lipschitz extendability constants, there are only two exact results. So conjecture. So there was a conjecture from Grünbaum from the 60s, 64, is that lambda 2, so when you only consider two-dimensional spaces, is the same as lambda of E hex, where this space is the Banach space, which has the regular hexagon as unit ball. So E hex is nothing but you take the regular hexagon, which I can draw now because I wrote it many times. So yeah, more or less. Regular hexagon. Hexagon as unit ball. So, and this was conjectured, and this conjecture has been proven 2009, proven by Chalmers and Levitsky in 2009. Okay, so from our theorem, we know that AE3 is smaller than lambda 2. here we use dimension of f of x is n-1 if the cardinality of x is n. So you lose one dimension. You lose one in this. So okay, so we have A3 is smaller than lambda 2. Of course, this is a very big canon because this is this is really not a straightforward proof. And so we have that which is 4/3. So now I can just finish by showing you that this lower bound is attained. And due to this, so we know what the maximizer is actually. So there's a very good candidate for which maps we can look for. So let x be x1, x2, x3 with a discrete metric with the dxy, xj, delta ij 2. So we have that here we have the points xy, x2, x3, and I can isometrically embed them in a tree. One, and here is M. And I can map the leaves F to here again, here I have E hex. And what I do, I just map the leaves to this triangle here. So yeah. So this is supposed to be fx1, fx2, fx3. And I want to extend the map to extend f to m. So to this point here, to the center of the tripod. And I think one sees it from the picture, it's really, there's only one sensible option. So one has to, this here, red dot, the red dot has to be f of m, and so f bar of m. And and you can show by a short computation lip for any extension f bar, you have lip f bar bigger than 4/3. So this is just a geometric argument. So that's the proof. And now we know that this implies AE3 is 4/3. So here it's really the big canon we used is this result here that lambda 2 is computed. And this is actually the only lambda which is known. The lambda 3 and lambda 4 are, it's not that clear. So lambda 3, there's a conjecture, but for lambda 4 already, there isn't even a candidate what the maximizer could be. So yeah, I think this is a good time to stop for the talk.
Thank you very much, Giuliano. Thanks.